Ladies and gentlemen, please welcome Morris Cohen. Stage
Much for coming. So we feel like the best way to celebrate the last 100 years is to talk about the next 100 years, which is a big task. But what better way to do it than to find people who are going to be around for a good chunk of those next 100 years. So this is our early career perspective panel. And to lead that discussion and moderate it, we have Jeff McHarg, who luckily represents the two sections that are here. We have the atmospheric and space electricity section in partnership with the space physics section. So thank you to Jeff for running the session for us.
All right, thank you very much. I appreciate it, Morris. Well, good afternoon, everybody. My name's Jeff. I thought I'd quickly introduce our panelists, and then I'll let them make their opening remarks. We've got Hazel Bayne and Nina Viavi, Eric Bruning, they're in the middle, Kristin Calhoun, and Merton. And I think what we're going to do is I will give a quick introduction, and then each of the people will give a quick 3-minute talk, and then at the end, we'll just open it up for questions. How's that sound? So first, we're going to have, thank you very much, Morris. First, we're going to have Hazel Bayne. Hazel is a research scientist at the Cooperative Institute for Research in Environmental Science at the University of Colorado up in Boulder and NOAA's Space Weather Prediction Center. She's currently specializing in the development of tools for operational space weather forecasting, and in particular, her work focuses on solar radiation storm forecasting. Before coming to Colorado, Hazel obtained her Master of Science in Physics and Astronomy and a PhD in Solar Physics from the University of Glasgow. And following her PhD, she spent 7 years at the Space Sciences Laboratory at Berkeley, where her work focused on hard X-rays and radio observations of solar flares and coronal mass ejections, as well as developing ground support software for an Antarctic high-altitude balloon. So you can't beat that. In addition to her research, Hazel's committed to creating a more diverse and inclusive science community. Hazel, you're up.
Okay, thanks, and thanks for inviting me to be on this panel. We were given 4 questions to think about when we were talking here, and one of those questions was, where do we expect to see AGU and the SPA section in 100 years' time? And that sort of time frame really resonated with me because that's a similar time frame, well, not similar, but close to a time frame that we talk a lot about in space weather forecasting, which is that we are decades, maybe 50 or 60 years behind terrestrial forecasting. And so when I started to think about how do we get there, I started to answer some of the other questions which we had, which was what data or computational advances would you have to solve your biggest problems? And I think a common theme in our field is that we need more data. It's very hard to validate our models when we have maybe 1 or 2 observations of the solar wind in a gigantic heliospheric system. It's hard to be able to know what the true real-time magnetic field environment is here at Earth and to know what those impacts are having on space weather impacts our Earth. And then that sort of naturally led me into this idea that I feel we're going to go in the direction of data assimilation, of ensemble modeling, of machine learning, where we start to really bring data and simulations together, that it's not just one or the other, that it's both together, and that our field would become a little bit less split into sub-disciplines of you're an observer and you're a modeler. And I think that to do that, we both need to use the empirical models, we need to use our physics-based models, we need to go back to fundamentals and really try and figure out how these big systems work all in one go, all the way from the sun, all the way out to the Earth, and not just treat it as, you know, these people look at the sun, these people look at the CMEs in the middle, and these people look at Earth. It is one system, and it all works together. And then I guess the other part of that question that they put in there, which I thought was great, was not only where do you see AGU and SPA being in 100 years, but also who do you see in 100 years? And I thought that that was a really great point to be able to bring up, that we need to diversify and be more inclusive in our science community. We need to be thinking about who we're bringing into the field, but not only that, how we are creating an inclusive environment for people to thrive in our field. We need to tackle issues like bias, like implicit bias. We need to talk about harassment. We need to talk about ways in which people can feel heard and which people can contribute, and that we can really get down to the science. We know that the best science gets done when diverse perspectives come together and can all contribute in that environment. And so I would really hope that in 100 years' time, I guess, not only from a science perspective, we're thinking about everything more like together and cross-disciplinary, but we're also doing that in terms of the people. And so I'm a little ahead of time, but I think I've said the main things that I want to say there, so maybe I will pass it on. Okay.
Thank you very much, Hazel. Well, you can already tell I'm not a very professional moderator. I forgot to tell you that we asked each of our speakers to pick one of our 4 questions and talk about them. You can read them up in the slide as we have now. Next, we've got Nicolene Viavi is a research astrophysicist at NASA Goddard Space Flight Center. She studies the sun, solar wind formation, and the impact of the solar wind on the Earth's magnetosphere. She earned her BS in Physics and Astronomy at the University of Washington and her PhD in Astronomy from Boston University. She was the 2018 American Astronomical Society Karen Harvey Prize winner and a recipient of the 2018 NASA Early Career Achievement Medal. She serves as the Solar Terrestrial Relations Observatory Stereo Deputy Project Scientist and as co-I on Polarimeter to Unify the Corona and Heliosphere Punch. Nicolene.
All right, hi everybody. So the question that I chose to focus on is, what process would you want perfect knowledge of? And if you had that, how would that change the world, science, or your life? And the process that I chose to talk about is magnetic reconnection. I think it's so fundamental to everything in the Sun-Earth connections. It's important for what I study, which is the sun, the solar corona, the solar atmosphere, and how it gets so hot, why it's millions of degrees when the solar photosphere below it is only 6,000 Kelvin. And we know the answer is the magnetic field, and we know that magnetic reconnection is playing a role. It might not be the whole story, but it's definitely part of the story. Additionally, the big space weather events like the coronal mass ejections and the solar flares coming from the sun, those also are come from magnetic reconnection. And so understanding the buildup of the magnetic energy, why magnetic reconnection doesn't happen, why it takes so long to build up that energy, all of those questions are of fundamental importance to the sun. They also are involved in how the solar wind is released when the solar atmosphere fills the solar system. Reconnection is involved in that process too. Again, it might not be the whole story, but it's definitely a really important piece of that story. Then when that solar wind or the coronal mass ejections get to Earth, there's more reconnection that happen in Earth's day side and then again on Earth's night side. So it's a fundamental universal process. I think it affects not just the Sun-Earth connection, it affects also the other planetary systems, it affects galaxies, it affects stars throughout the universe. So this is one of those fundamental universal processes. Now there's been a lot of important advances that have happened recently with the MMS mission in Earth's magnetosphere and understanding how magnetic reconnection takes place in that environment. I think what we need in the future is how does it take place in other environments? Does it look different or the same when we're on the sun, when we're in the solar corona? It's a very different plasma environment. Does it look the same or different when we're in other stellar systems? So I think that would be really important for ultimately predicting space weather and really understanding the fundamental physics that affects the Sun-Earth connection. And I'll stop with that.
Thank you very much, Nicolene. Well, I'm really impressed. You know, it's really fun to take part in this because we see everything from outer planets to the solar wind, and now we're going to move a little bit closer down to the Earth. We have Eric Bruning. Eric received his Bachelor of Science and his PhD from the University of Oklahoma, where he worked after that he worked at the Maryland's Cooperative Institute for Climate and Satellites and the Earth Science System Science Interdisciplinary Center with GOES-R Geostationary Lightning Mapper program. He's currently an associate professor in the atmospheric science faculty at Texas Tech and Eric specializes in the relationships of storm electrification and lightning to the thermodynamics, microphysics, kinematics, and dynamics of thunderstorms. He received an NSF Career Award to relate the distribution of lightning flash size and lightning initiation to the deformation of charge structures by turbulence in thunderstorms, and has worked with a painter to develop a public art exhibit depicting this relationship, which I think is really interesting. Since 2018, he's developed and supported the data processing method used to create operational displays of GLM data. Eric, take it away.
All right, thanks for inviting me to talk a little bit about my perspective on things. One of the questions was related to computational capabilities and challenges, and I wanted to address that theme a little bit through the lens of trying to take the atmospheric electricity research that I do and the data sets that we have there that have these very fine time resolutions, sometimes down to the nanosecond scale, that cover large spatial areas potentially, and we might even aggregate them up into multiple years. And trying to blend those together with other meteorological data sets. And I found computing to be a real benefit in being able to do that, but also a challenge in working with those tools at times to bring together those data sets. So I wanted to turn a little bit more towards a general comment about scientific computing and how we might benefit those sorts of synthesis activities over the next 100 years as we bring together all of these different disciplines that are active within AGU and beyond. And I think the tools that have worked best for me are those that they can be very flexibly combined, and I think that comes from, it's tied intimately to this idea of discovery that we all want to make as scientists, where almost by definition we don't really know how to process or work with the data we have in order to find out what we want to find. And I think I want to contrast that with a lot of scientific computing initiatives that are even very well resourced that might try and define a specific problem ahead of time and develop a sort of framework for addressing that specific problem. So instead, I want to advocate for this idea of this sort of toolkit, a screwdriver and a hammer instead of a whole building, so that we can empower people to work with any sort of data set that they wish to bring together. I think I wanted to reflect in my last little bit of time here on machine learning and artificial intelligence and these cloud computing and big data, things that are very fashionable and in vogue right now. And what I'm really interested to see emerge from those efforts is sort of that next step of generalizable tools that we could apply to lots of different sort of problems, instead of focusing on them as a magic bullet to engineer a solution to a specific problem. So, we've already benefited a lot from programming languages that let us work with arrays of data very fluidly, and I see that coupled with some of the automatic differentiation things and the ability to exploit large computing resources for much more general purpose problems is a potential benefit there. Thanks.
Well, I'd like to introduce Kristin Calhoun, who received her PhD from the School of Meteorology at the University of Oklahoma and is currently a research scientist at the NOAA National Severe Storms Laboratory. If you've never been there, you should really go. It's a tremendously interesting place to visit. Her work focuses on applied research in the transition of severe storms research and algorithms to the National Weather Service operations. Kristin has been principal investigator on numerous projects within the hazardous weather test bed, including the development and testing of multiple lightning integrated and data assimilation algorithms. Additionally, Kristin is on the science team for the Geostationary Lightning Mapper, GLM, where she helps guide the operational implementation and use of the data for severe weather forecasting. Her current research is investigating new paths to increase the impact of data from GOES Advanced Baseline Imager and GLM when blended with other operational data sets to further the understanding and forecasting of severe and convective storms. Kristin.
All right, so thank you for that introduction, Jeff. And a lot of people have covered a lot of nice topics today. I wanted to bring it back to earth. And as I thought about these questions, I really wanted to focus on what brought me into the field at first. And when I thought about that, when I was 5 years old, I was scared of thunderstorms. And it was the loud booming from the thunder that freaked me out. And I remember my dad told me, it's not really the thunder that you should be worried about, it's the lightning. And through that, I kind of built my career knowing that I wanted to be a meteorologist, and came out to graduate school at the University of Oklahoma and got into lightning studies. And then as part of that research, we got out in the field and released balloons with electric field meters to get charge profiles of storms. And if you think about lightning safety, maybe the middle of a field underneath a thunderstorm is not the best place to be. But we can learn a lot of neat things through that process of taking kind of experiments and taking a risk in what we can learn. So I originally had a comic on here from XKCD, but it's the idea of what fields of study are you most likely to die from what you study. And of course, gerontology and a study of old age is up there, and I think volcanology was up there, and somewhere in the back was meteorology. And then I thought, well, a lightning scientist studying that is maybe a little bit higher on that risk route. But so my own work, I'm really interested in understanding more about lightning so we can save lives. So that's fundamentally been my interest in how we can forecast lightning. Now, at the Benjamin Franklin lecture today, Joe Dwyer introduced a lot of fundamental questions of things we don't know yet, and there's a lot, from how lightning is initiated to where it propagates to ground. There's a lot we do understand, and it's what we can think about moving forward is, if I could fundamentally answer a question, it would be that prediction of understanding where lightning comes to ground. So we can move with things like machine learning, and as Eric talked about, blending data assimilation, and begin to use both the meteorology and what we understand from lightning physics. So I think about AGU as we develop and over the next 100 years, one thing the atmospheric electricity group really benefits from is a combination of lightning physicists that really studied like the fundamental propagation of lightning, the initiation process, the streamer process, a lot of nitty-gritty details, but also blending that with myself and Eric and others who work on the meteorology and understanding what's going on in a bigger scale that helps create that charge. Why are the microphysics driving what they are? And then if we understand more about that process, we can even hopefully use that information to help with other features when we talk about severe weather. So not just lightning as a threat of itself, but helping understand severe storms as they change and develop, and then bringing that into things like warning operations. So I would hope in the next 100 years we can continue to build that kind of diversity between different people and different groups, and kind of fundamentally see things from a different point of view, and then collaborate to bring that kind of holistic viewpoint together.
Thank you very much. Well, Merton recently received a PhD and is now a researcher at the Alakhanyan National Science Laboratory of the Yerevan Physics Institute in Armenia. Her research is devoted to the investigation of thundercloud electrification processes and thunderstorm ground enhancements, TGEs, of energetic radiation. She's also interested in the global electric circuit and electric field measurements. In 2018, HRMC founded the Yerevan Young Minds section, which is a branch within the European Physical Society projects. HRMC.
Thank you. Actually, today, all my colleagues has answered the question, or raised the question, and I will just somehow sum up of them. Here, I have bring the one of the photographs of our station. It's high mountain stations located on Aragat. Even in hard conditions, the station is operating and giving us lots of opportunities of investigating atmospheric phenomena. And if we will merge ground-based measurements with measurements done in upper atmosphere and in general, we will have a great platform to investigate different phenomena which are crucial for nowadays life. Like Earth is changing, and for having a good life and having everything is better, we need to answer lots of questions. And so I find very important that scientists work for a society and make science more closer to the society, and do steps for making more like important questions, more important questions to solve them. So here is the very famous quotes from the Max Planck. An experiment is a question which science posed to the nature, and the measurement is the records of the nature answer. Taking account that humans tend to go to the beyond the Earth and go to the Mars and Moon, I think that in the next after 100 years, the EGU will not take place in Earth, but it will be on somewhere in another planet, and we will call it Interstellar Geophysical Union. Thank you.
Well, thanks to all of our panelists, and I think it's time for us to turn the floor over to you. We'd enjoy taking questions. I think we also have some questions that have come in from outside our local area via the app. And so if someone's got a question, we can't really see from up here, but raise your hand and perhaps they'll bring you a mic. Anyone? Oh, I think over here on the right I heard. There we go.
So some of you talked about societal benefits, and we're working more on that within AGU and across society. But what do you see as a potential, a potential great advance in that societal impact in the next, I don't know, 20 years, 40 years, 100 years? That's a general question. I don't know if you all want to answer it, if somebody wants to offer, somebody that mentioned the societal benefits. Maybe Ripsy.
I'll go ahead and start. I think risk communication is one of the biggest kind of both hindrances and possible opportunities we have in terms of communication of what we know as scientists to either the risk or the potential for other people. I think that's true, as we approach any kind of disaster or natural hazard, especially through what may be occurring over climate change. I think we have a great opportunity. I'm going to swerve that question, apparently. With now like the geostationary lightning mapper and other satellites that have now launched, we can see lightning from space. We can begin to get a record of what's going on over a number of years and begin to understand kind of how that changes over time, and then being able to communicate that and seeing the societal impact and understanding of how things like lightning are changing over time over a warming planet. So sorry to swerve that so much.
I think now we are living in the time where the problems are very crucial for the scientists because in some countries it's very hard to explain for what is the science. So some of the governments or the representatives of the politicians, they thought that the science is like just additional waste of money. So I think that we need to be more close to the community to solve the problems which are, actually the scientists are solving the problems, but we should show them how the importance are there and be more active in that field as well. So maybe some others will have some ideas.
So I guess a lot of our job is thinking about our customers and the societal impacts that space weather has on them. And that's something that's really increased in the last 10 years, especially sort of at a congressional level, is trying to really put forward what those impacts are. I mean, some of our customers are the electrical grids. We have aviation. We just started some forecast advisories for the aviation community to guide their navigations, their communications, and their radiation effects on flights over the polar routes. A big thing that's going to become a much bigger thing in the next few years is that as society and technology moves into space, those systems have a dependency to survive space weather. And so that's something that we have to provide to our customers in the satellite community, is when to take action to perhaps mitigate some of those effects. And then going even further than that, as NASA starts to think about going back to the moon and moving further to Mars, we need to really start thinking about forecasting for other parts in the solar system. And really, to get to Mars, we need to solve that problem of the radiation, or at least be able to forecast with some skill. And so we saw what a large societal impact going to the moon the first time was. Going to Mars is going to push that even further. So.
Hazel just mentioned some very ambitious projects, and I think that's something that I'd like to see us as scientists try a little bit more of. It seems in some ways we've lost our swagger in a way, and should be saying things like Kristin hinted at, like how could we predict lightning, and I think that's very, as a scientist, I want to say that in a way that's very fundamentally grounded in the sense that this is a real physical system that has real physical laws that are, that the lightning's following, and that by maybe trying to frame a bigger question, it drives us to probe more deeply than we would otherwise if we were, pursuing safe funding routes that were, easier to articulate. But that I think requires a degree of community consensus and support, and I think AGU plays an important role in that, and giving us an opportunity to gather and discuss with one another, frankly, things that we might not say in public for fear of sounding crazy. Like, I think we might predict lightning in the next 20 years.
All right, so what is my answer? I think space is big, and making the connection between all of the different places in space, from the sun to the Earth, is what I've been thinking a lot about, and that's the sort of the space weather applications that Hazel talked about. But also the sun to Mars, that's even bigger, and a lot happens between the sun on the way to these places. And so understanding the full system and having enough computational power to really model that full system from the smallest scales to the biggest scales and how they couple back and forth to each other. And then the data coverage to really understand all those different interactions is what's needed so that we can really have predictive space weather, which is ultimately what's going to make all the benefits that Hazel talked about for society.
Well, great, thanks very much. Do we have another question from the audience, or do we have one that we could maybe, here we go, back in the middle.
I have a question that in some ways is a finer point on what was just asked, and in other ways is maybe a little broader. It's been said by many that we're living in a post-truth world in some arenas, and we at AGU we've all devoted our lives to the notion of truth and investigating the world around us through science. What's your take on how we can be that beacon moving forward, if you will, re-evangelize science to the world? Not necessarily through direct application, but through who we are as scientists. Any thoughts?
I think I saw a statistic recently that said when you surveyed the US population, actually public opinion in science hadn't actually changed, but the voices on different sides were getting louder. And so in some ways I want to say we need to keep on doing what we're doing, but I think we also need to continue to evolve, and we need to continue to engage with the public. We need to continue to engage with government. We need to get out there and tell our truth, tell our story. And I think that we need to adapt and change our methods of communication in order to do that.
Yeah, I think we need to communicate. I think that's where, I think there's been a lot of innovation and new ways to communicate, but we're behind the times. And I think there's a lot of research that shows what effectively communicates points. Companies have been doing this for years to advertise their products, to get you to buy their products. And so there's a lot of data actually on what people respond to and what they connect to. And I think we should be taking advantage of some of that research to get our messages across to all of the different stakeholders.
And I think I'll add that visiting different sections of AGU, and I've jumped into some different talks in different groups, everything that people are doing is really cool. And I think, getting into early career and then going out to STEM and all the way through, supporting people as they come up through their career and saying, no, it's really cool what you're doing, and bringing people in, and then supporting them not just early career, through the, K12, but as they go in and through graduate school, and as we continue to support people all the way through their career, I think there's an impact on just how many people this can reach. But yeah, I think K12 education and just showing a lot of how much cool stuff is being done by scientists can help get an appreciation for what science is and what it can accomplish.
I think building off of that, this idea of engaging with the public, not only to provide answers where we have them and ensure that those answers are communicated clearly, but also to help them, to help the public, and I think I feel this especially at a university, to have them join with us in that sense of curiosity. Of course, we don't expect everyone to have maybe the technical skills that we have in ways, but I had a conversation with a staff member that takes care of my lighting instruments the other day, and he comes from a different sort of political sensibility, but we both share this sort of rampant curiosity about things. And so even though we were talking about climate change and some very difficult issues, we're able to connect on that shared sense that the world we're in is interesting. And so going back to K-12 and university level and ensuring that that curiosity is seen as a part of a good society is a thing I think is important.
In my point of view, we should develop our skills to sell our ideas. Like even the scientific research, even scientific ideas should be sold to these stakeholders and to interested parties. And it's very important to find a way how truly and correctly show it. So I think we need to communicate more in that way.
Well, let's see. Do we have a question from outside the audience that has come in through the app? Does anyone have that handy?
We do. We have 5 questions. The one with the most votes that people want to hear the answer to is, as early career scientists on the Inspire stage, what inspires you to continue your research and work?
We are also inspired, obviously. So I study the sun and the sun-earth connections, and it's just amazing. The time right now is ripe for all of the computational advancements, but also the data that we're getting in with Parker Solar Probe, and Solar Orbiter is going to launch in a couple of months, and of course Punch in a couple of years, Craig. And I think it's just the opportunity is to really get all of the data and put it together in ways that we haven't before. Not just single points and not just single images, but putting it all together and building a global picture to answer some of these questions. It's just a really cool time to be in space physics.
I have two little boys. They're 5 and 3 years old, and the littlest one, the 3-year-old, is probably more scared than I was of thunderstorms at his age. And so he inspires me almost on a daily basis, especially in Oklahoma where we get a lot of strong storms. And so there'll be a lot of nights that he'll end up visiting me in the middle of the night because he's scared. So I'd say my kids are kind of a daily inspiration for me.
Actually, it's very inspiring to now answers of the questions. When someone is approaching you as a scientist and asking very simple question for you, but when you are looking on their eyes and see that it's very difficult for them to understand, and you are explaining it, and it's so inspiring for you. And being scientist is meaning for me that in the future, or maybe tomorrow, or maybe, I don't know, 5 years ago, I will discover something. I will add some knowledge on basis of which we need it for the developed Earth and having developed community.
I've been trying to think about this while other people have been answering, and it sounds like we're all inspired by other people, which is, for me, I'm inspired by the fact that our customers want something from us. Like, they want us to solve their problems, and it's immensely gratifying to be able to do something that someone finds useful. And especially with the whole Artemis mission and stuff going to Mars, I find that incredibly inspiring that some part of this community here at a geophysical meeting could actually push us towards having boots on the moon again and having somebody or maybe just for the moment robotic stuff going to Mars. It's other people that sometimes present those challenges, and it's always nice to try and solve them.
Also, I would like to add, if someone is do not decided yet to go into deep to the science, I would like to say, don't think anymore, just go, because you are like artists which is inventing all the time, and it doesn't mean that you will like just sit in your office and work with the graphs, with the codes, and it doesn't it means something more for other people as well, and you will just create something new.
I also want to add, maybe for the kids that were really, really nerdy like me, I got into meteorology because I liked all of the math, and I wanted to be able to play with computers and maps all of the time. And so I also, would probably say to any of the, kids in an elementary school, like if you find yourself getting excited by those things too, that's okay. And there's a very gratifying career there for you as a participant in science.
Well, I was struck, we're here at AGU, and I'd like to know, what has AGU done that changed your life? And looking forward as the new leadership in AGU, what do you think you can do to further the next generation of scientists?
I guess I'll start. I was fortunate to be involved in a research group as an undergraduate that encouraged me to go to AGU as an undergraduate. And I think getting to a national level meeting so you see what the best work is at a very early, at a very young age is a really great way to calibrate the future of the field, which is those students. To what it looks like to do world-class research. And I hope that part of what they encounter when they come here at AGU, and this is certainly what I found, is that there's a welcoming interest in connecting as humans in the conduct of research and in our discussion of the research here at the meeting. And in some ways knowing that you've seen the best and that everyone's still talking to you can be tremendously powerful.
I think the thing that I love about AGU is the fact that we see other subfields and that they're solving sometimes very similar problems to what we're solving. And that can be down to the level of How do you handle lots of data? How do you handle bad data? How do you do new machine learning? How do you do data assimilation? Like several people on here talked about that. But I think also connecting with other people in other sections to figure out how we solve those issues about diversifying our field, about making it more inclusive. There are some kick-ass people in some other sections that are really leading the way in that, and AGU has taken big steps forward that I think that we, when we go back to our subfields and have subfield meetings and workshops, can emulate those things. And AGU has the power behind it and the money and the people behind it to push that forward.
Yeah, just to echo what Hazel said, I think what AGU shows you is that you don't have to reinvent the wheel. There are solutions out there that other people have figured out, and sometimes the best thing is to use a solution that already exists and adapt it to us. And there are so many different models of solutions here for everything from the scientific application and the computation to how do we do science better and how do we encourage more people to join the field.
I just want to add that it's a huge networking place that where you can meet a lot of different scientists from the different fields, and it's helping you not only to focus on one specific question topics, but arise new ones.
All right, well, do we have another question from the audience? I can't really see up here, so perhaps...
Here we've got one right here. Hold on.
As an undergraduate coming to AGU for the first time as a junior, do you have any recommendations about how to go further in the field and get into grad school and all the big questions that I have?
I guess I'll take that one as the one who brought up undergraduate attendance. I think that the most important thing is to keep showing up. So the first poster I gave here, people walked by and were like, huh, it looks like you did some things. And it took me a lot of years of persistence to be to the point where I guess I'm communicating well enough what I'm doing that I'm sitting up here talking to you. So certainly keep at it. Don't hesitate to visit with people. By and large, I've found the atmospheric electricity community to be very welcoming. There's certainly stories I've heard that are not as welcoming, but by and large, I would really encourage that to not hesitate to visit with folks.
So I would say, I remember when I started grad school, and which is a little bit further, but anyway, undergraduate was a couple of years before that. And I remember failing for the first time, and then failing again, and having the wrong answer, and things just not working out. And my dad said something to me that was really important, and I've definitely come back to it again and again over my career, which is, as scientists, we should be wrong most of the time. If you're doing new things, if you're really pushing the envelope, if you're really trying out ideas that people haven't been doing before, it shouldn't work right away. It should be difficult, and you should have to try again and again and again. So perseverance, I think, was the word you used, and I think that's really important. Stick with it.
That's like the old saying, before you're old and wise, you have to be young and stupid.
And one more thing, just ask lots of questions, as many people as you can. You will discover lots of new things for you, and you will decide which part of the science you want to cover.
Well, that's great. It looks like we've got about 8 or 9 minutes left. We could probably take another question or two if somebody has a good one, or we could try to go to outside of the local hall.
So the question online that most people want an answer to right now is, which Avenger are you? So which Marvel character, which Avenger are you?
I have no idea who any of them are.
I said earlier I was that nerdy kid who really liked the computer. I don't watch the Marvel movies, so yeah.
I don't know who the Avengers are, but I did see that TikTok where they're all jumping out of the water, and that was awesome.
I have 2 kids who are 7 and 5, and so the most recent thing I've watched was Mary Poppins, and that's most of what we watch.
I do know the Avengers, and I've watched all the Marvel movies. Gosh, I really don't have a good answer for who I see myself as. In a sense of sarcasm where I tend to go to maybe Black Widow in some ways. But the relationship's not necessarily there. Captain Marvel's also super cool, and I wish I could be that cool. So, sorry I didn't give like a great answer to that. It's not something I've thought about in my regular life. Who do I relate to most in the Avengers? But it's kind of a cool question.
We have another question online if you want to take one. What structural or institutional changes need to happen to pave the way for a more diverse and inclusive future for our fields?
I kind of hinted at this at an earlier question, but I think, for myself, I felt pretty confident as a woman in science or beginning science, even through undergraduate, when in the meteorology class it was like 80% male and 20% female, I was still okay. As I got to graduate school and began to see some impacts going out to kind of conferences like this and setting up things, and one time I was asked to take care of food, and other people around me who were at the same level were asked to talk about the science. That's when I started to notice and felt a little bit inferior. And so for me, I think a lot of times we help try to elevate STEM for all sorts of students in diverse backgrounds, and I think that is absolutely a route we need to continue. But I feel like sometimes we drop that as we get to graduate school and beyond, as we move through early career to later career. There are a lot of different things that can kind of be a roadblock for different people in different backgrounds, whether it's due to gender diversity or whether it's due to kind of backgrounds in more of a poverty level and where the funding comes from and where you're used to asking for things. So I think we need to do a lot more as we talk about kind of continuing that path for graduate school and beyond in the career to help with diversity and inclusion.
I think also we need to get past this idea that it's just about gender. And almost every committee I've been on, they say we have so many women on the field, and that in speaking, and we need to get past that. It's not just about women, it's about other minority identities, it's about race, it is about accessibility, it is about economic status, it's about many different things, and people at the intersections of these identities are suffering worse than those just in one or the other. And we need to challenge our institutes to take this seriously, to stop and not just give it lip service and not have a token person on the panel and not just have a token speaker, but to really care about why we're doing this. And that needs to be built into everything that we do, because if we're not creating an environment where everybody can be heard, then we're not going to solve the problems of our generation.
I think I've been in the field, I graduated about 10 years ago, and I've already noticed a lot of progress. When I first came to AGU did not have an official harassment policy, and now they do. Same with the AAS, same with NASA, same with NSF. So there's been a lot of very positive movement, a lot of very positive growth. I don't know the answer, but I think we need to keep having the conversation all the time and keep evaluating if the things that are happening, if the actions that are being taken are making the progress go in the correct direction.
And I will say that's not just at the institutional level. That should be for every single person that is sitting in here, is to think about that. Every time you have an opportunity to make a change, speak up and say something, because change will happen both from the grassroots level but also at the institutional level.
If I could go in a slightly different direction with that as well, you should listen to what my colleagues are saying about all of those issues, because they've covered them well. I think there's other structural things that also crop up that relate to things like socioeconomic diversity and privilege of access to tooling and those sorts of things. So I mentioned scientific computing tooling before, and I've been one of my reasons for really getting into the open source mindset of doing science is that a lot of those tools are free. So I can go to a colleague anywhere around the world and give them my approach for processing this geostationary lightning mapping data, and it opens that up to them. And thinking about this future that might be big data and machine learning, I think we would benefit as a community from thinking very carefully about the degree to which those solutions, which are largely being driven by large companies right now, are promoting ownership of the science by the community, as opposed to serving as a form of capture of an approach to doing science for the people that can afford to go to those big tools.
Actually, listening to my colleagues, I understood that really from one country to another country that the problems are different. And just from my point of view, I just want to mention that we should remove disappointment from our life. Like, scientists should not have, disappointment from some kind of not good results and so on, but disappointment of continuing to do the science. It's very important, and I would like to mention that in some countries, some small countries, there are, because the scientists has really focus on the work, and they need the support.
Well, that's great. I really appreciate all of your comments and your insights. I think we're about at the end of our day, and I thank our audience for attending. I think the panelists will be here in the local area, so if you have some questions you'd like to ask in a personal level, please feel free to come up afterwards. Morris, I think we're going to turn it over to you to wind it up.
Yeah, I've nothing else to say. Thank you, Jeff McHarg, for moderating this panel. Thank you to our panelists for agreeing to this grilling. I don't know about all of you, but I can't think about what tomorrow is going to be like for me, let alone in 100 years, so that's certainly a difficult thing to do. And also thank you to Christina Cohen for co-planning this along with me. And enjoy the rest of your day and the rest of your AGU. Thank you.